Okay, thank you. It's a pleasure to be here speaking at the European Lunar Symposium. I'm Bethany Ehlmann, professor of planetary science at Caltech and principal investigator of Lunar Trailblazer, which is our pioneering small satellite to study lunar water on the moon. The goal is to understand the form, distribution, and abundance on the moon. So we were selected as part of a new kind of NASA mission, the Small Innovative Missions for Planetary Exploration back in 2019. So lower cost, higher risk approach to doing excellent planetary science. And one of the most important questions is water on the moon. Now, we are addressing this from orbit, collecting those base maps that will hopefully inform a number of landers of the future, and are doing that using a combination of reflected and emitted light measured simultaneously with the two instruments on our ride-along spacecraft. That's the high-resolution volatiles and minerals moon mapper and imaging spectrometer from JPL that will get composition from 0.6 to 3.6 micrometers. So both the iron-related mineralogy of the moon as well as that 3 micrometer feature related to water. The Lunar Thermal Mapper instrument provided here from here in the UK, University of Oxford and the United Kingdom Space Agency, is going to be mapping the thermal composition, the temperature of the moon, as well as the composition in 11 different thermal channels centered around the silicate features. So we are a rideshare mission. We fit in an ESPA ring and we'll be launching at the end of this year with Intuitive Machines Lander number 2, along with the payload of the last speaker we just talked who is on the lander. We are riding along, getting a ride out of Earth's gravity well on the way to our 100-kilometer polar orbit. So Rachel Klima is also here, Deputy PI, and then JPL is the Management System Engineering, Flight System by Lockheed Martin, and Caltech is our student collaboration. So we are really going after some of the science that was revealed first really in the around 2010 or so, the first being sunlit water that is on the warm parts of the moon, as well as this question of water and water ice in the permanently shadowed regions. So, you know, we in this room are familiar broadly with the latitudinal dependence of the signature of the 3 micrometer absorption due to OH or H2O, as well as the hydrogen enrichments and in some cases spectral signatures of water ice. But of course, there are significant questions about how much is there. What is the form and why does it vary? So this is just some modeling by Josh Banfield in the 2015 paper showing that depending on which thermal model you use, that actually profoundly impacts how much water you estimate is present. And furthermore, in many of these locations where M cubed is, one of the challenges is, you know, it was not expected to be a water finding orbiter. So one of the challenges, we don't have the wavelength coverages to get the form, but this is where Lunar Trailblazer comes in to get that longer wavelength to distinguish what exactly is this water on the sunlit portions. Similarly, we've seen that when we actually peer into areas where there are M cubed spectral signatures of water ice, where there are hydrogen enrichments, it's non-obvious in shadow cam data, where is the water in this image? Is it perhaps all in the subsurface, or is it there on the surface just at abundances less than about 20% so that we're not seeing the albedo contrast? Lunar Trailblazer is going to be sensitive to water in these shadowed regions. And so the goals are to understand the form, abundance, and distribution of the sunlit water, to measure for time variation. We'll be getting images at up to 3 times, even more than 3 times per lunar day of select areas to determine the form and abundance of ice in these permanently shadowed regions, and to understand really how temperature interacts with ice by the simultaneous measurement of temperature and water with the 2 instruments. Of course, I should say, you know, the bonus is that this will benefit all landed missions to come, both for the water questions, as well as those compositional and geological maps for exploring questions of igneous processes. So the nature of the data set is they are footprints of about 20 kilometers or so where the data are nested. That is, there's an imaging spectrometer cube that for every pixel has a spectrum associated with water and iron mineralogy. And overlapping from Lunar Thermal Mapper is temperature maps, as well as being able to distinguish the silicate composition. And so here are the 11 channels with the 3 channels from Diviner that originally discovered some of the silicate, some of the profound silicate variability over lanes. So we'll be able to discriminate those at a much greater degree and higher spatial resolution for a few select areas, about 2% of the lunar surface. Now, you might say an imaging spectrometer in the visible shortwave infrared, well, that's reflected light. You're looking at permanent shadow. How are you getting any light out of the permanent shadow into your instrument? That is a good question. That is, in fact, the most stressing requirement of Lunar Trailblazer is the ability to use the terrain scattered light, that is light that comes in, that bounces off the walls of the craters, then onto any ice deposit on the floor, and then back to the sensor. Our requirement is that even for a 1% band depth, that we're able to confidently make the discrimination between ice and other materials. Fortunately, we've built the instrument and we know that it achieves the signal to noise performance that will allow us to do this. So imaging spectrometer, right, light is coming through, is rows in an image line being split to get that spectrum. It is always very gratifying as a principal investigator when your finished instrument matches the PowerPoint and shows really the level of performance that's necessary. And this is post-vibration testing, just shining a flashlight in for the aliveness testing of HVM cubed on the other side of our vibrations. So Lunar Thermal Mapper, similarly, our University of Oxford instrument built, delivered on the spacecraft. So grateful to the United Kingdom Space Agency and to this great partnership in science and exploration that'll enable us to get simultaneous temperature along with this water. Similarly, it's great when the instrument looks like the CAD. So the light comes in, goes through the telescope. The filter assembly is placed sort of at the midpoint of the focal array, a plane array here, and then goes back to the detector that you see here. And flight instrument complete, as well as happy PhD student Rory Evans getting signal through from the instrument. So our flight system built by Lockheed Martin, it's a small satellite, as I mentioned. So it's about 3.5 meter span as we're going, and 250 kilo. Here you can see us in the rideshare envelope on the ESPA ring. Just to give you a sense of the progression of the build, it's always fun to look at spacecraft photos. As of last fall of 22, it was, harnessing in panels, looking at it, waiting to get put together. And over the last nearly 2 years now, from the wheel-in of the propulsion system, the installation of HVM cubed, thermal vacuum testing, and then installation of the Lunar Thermal Mapper instrument, and then finally spin testing. The wheel-in here to move in for vibration testing, and here on the vibration table. Now, Lunar Trailblazer has not been without our challenges. One of the reasons you vibrate a spacecraft is in order to break things on Earth so that you can fix them before getting things to space. We have been very successful with that. So we're in the process now of doing some rework of our main engine following vibration tests, but are on track to finish that in August and be prepared for a ship to Cape as early as early October. So in the meantime, we've been setting up our operations at Caltech, and something that's, I think, relatively unique, if not unique about planetary missions is that entirely soup to nuts, the operation is going to be based at a university. So we're leveraging the fact that Caltech IPAC is an organization that's successfully done science operations for space telescopes, for the science instruments on them. Not only are we operating, in this case, the science instruments on Lunar Trailblazer, but really the entire spacecraft. So it's been an effort to transform fairly normal looking office space into a proper operations center. And one of the other features of the mission is that because we're at a university, we are able to train the next generation of scientists and engineers, and have had 35 undergraduate students as part of a NASA-funded student collaboration from Pasadena City College, a local community college, as well as from Caltech, participate in all aspects of operations, from design of telemetry, from communications of tests with the Deep Space Network, to designing some of, if you check out our website, some of the science graphics and products. So it's really an opportunity. Students help with the low-cost mission part of it, but it's also a really important role to train the next generation, and they will be on console when we launch later in the year. So as mentioned, we're orbiting, we're push brooming along, we're collecting targets. You can check out our target map. It's fully online. Make sure your favorite place is there. If your favorite place is not there, come see me at this meeting, because we do have the opportunity to have guest targeters from the community. We had one round of community targeting efforts just before our preliminary design review. And once we're launched and in space and in cruise to the moon, we'll have another round of folks to be able to enter in any of your targets that you might want on the moon that are not already on our target coverage map. The nature of it is that as a small satellite, low-cost mission, one of the things we're most limited by is the capabilities of some of the system. In this case, we are fundamentally communications limited. That's not why we're not, paintbrushing the whole moon. We're acquiring these selected targeted images, and, we get anywhere between 1 to 12 per day, depending exactly where we are in the lunar surface. In terms of mission phases, launching at the end of the calendar year is anticipated. Then an early, very intense period of operations where we have 3 or 4 trajectory correction maneuvers in the first week. Cruise looks very complicated, and that's because it's a low thrust, low energy trajectory. We don't have, the hefty engine to do an Apollo style burn. In fact, we have to miss the moon and then work our way back. But after anywhere from 5 to 7 months, we work our way through a period after a lunar orbit insertion burn, do the period reduction to work our way into the science orbit, where we have in total for phase E from launch to science orbit 2 years of operations. Now, a feature is that which trajectory we end up on and how long it takes us to get to the moon is highly sensitive to the day we actually launch. So here are just a few examples from some notional times as to what the trajectory looks like. It's quite different, and it's very interesting. We'll know once we launch which one that we're on. So to finish up and sum what lies ahead, well, we've had a lot behind us here. We're all the way through to flight system nearly complete and gearing toward launch at the end of the calendar year, where we'll be on a SpaceX Falcon 9 as at the bottom of the Intuitive Machines stack on an ESPA ring. So I will say that we are going to provide data that are optimized over what you see here, which are some of the illumination maps, but Lunar Trailblazer will be actually allowing them to be water and rock composition maps, mapping the form, abundance, and distribution of water. So driven by important science, thank you to NASA, thank you to the United Kingdom Space Agency for supporting the mission. We're at the start of an exciting journey, and hopefully this data will soon be available for lunar science and exploration. Thank you.
Thank you. Thank you, Bethany. We have time for one major question here, I think, from a remote link. So please.
Maybe it's better if you read it out loud, because
This is a very long question.
Yes.
Okay, let me try to read it first and then summarize. If you have confirmed the presence of less than 1% water in its distribution, and maybe even the D to H, what scientific understanding do you expect? Just the form, abundance, and distribution of water is not science. I agree. I actually agree with that very strongly. So I think finding the amount of water in the form, abundance, and distribution is, first of all, the start of doing science. Because I think one of the biggest questions is, where did the water come from on the moon? That is it sourced from the original water on the moon during accretion? That was there from accretion, perhaps then released from volcanic outgassing? Did it come from later delivery from asteroids or comets? If so, in what proportion from asteroids or comets? The way that we get there, right, is first by finding the water, then you might want to go check out the isotopic signature of it, which will allow you to differentiate these hypotheses. I think in the best case, Lunar Trailblazer might provide some additional data because one of the things that can differentiate these, and Kathy Mant and Dave Page and Zhang and Page have talked about this, you have different volatiles accompanying the water. If you have a lot of lunar volcanism, you might expect sulfurous ices and carbon dioxide ices. If you have a lot of cometary input, you might expect ammonia and carbon dioxide. In the luckiest case, actually, Lunar Trailblazer has the ability to see these other ices. So if they're there, we'll see it. So those are just some of the ways that it contributes to science.